So today we're going to start with chapter 20, which is nonlinear circuits. So the first thing we're going to talk about is what do we mean by linear versus nonlinear circuits? And then we're going to look at comparators with a zero reference, comparators with a non-zero reference, with hysteresis, and something called window comparators. And these are sections 20.1 to 20.4 in the textbook. So chapters 16, 17, and 18 were about linear circuits. And what we mean by a linear circuit is that when we provide an input, let's say in volts, and we get an output also in volts, that the response or the relationship between V in and V out is a line. So that the V out is equal to some multiple, some gain factor, times what's coming in. So that is a linear circuit. The input-output relationship is a line. It's a function of y equals mx plus b. Now this doesn't have to be V in versus V out. We could put in volts and we could get current out. So that would be a voltage to current converter. And we can make that with a non-inverting amplifier like so. So we put 100 ohms down here. When I put 1 volt there, current will flow here. So this is 1 volt, which means I'm putting 10 milliamps through this resistor. And then 2 volts would give me 20 milliamps and 3 volts would give me 30 milliamps. So it's a linear response. How much current we get out is a straight multiple of the input voltage, but it's not a gain factor. The relationship between input and output is basically I out is equal to something times V in. And what is the something? Well, we know that I equals V over R, so this something must be 1 over R. That's what we're multiplying V in by to get current. And that is a conductance. 1 over R is G, and that is a conductance. So this graph is a conductance graph. So a linear circuit may be a straight gain where it goes volts to volts, or it could also do a conversion where it goes volts to amps or amps to volts. But a linear circuit means that the relationship between the input and output is multiplied by something, and what you've got is a linear relationship between the two. Chapter 20 deals with nonlinear circuits. In a nonlinear circuit, then the output is not always a straight multiple of the input. Let me give you an example. Say we've got a relationship that looks something like this. V in and V out, so it's a volts to volts relationship. But let's say we hit some certain value, 5 volts, and all of a sudden the output snaps up to the highest maximum value. So positive max. And then when we hit minus 5 volts, it snaps down to some negative maximum value. So here the relationship between input and output is not a straight multiple of one thing against another. There's conditions and thresholds that occur that basically we get 3 different outputs depending on where we are. But here between minus 5 and plus 5 we get the same thing, and greater than 5 volts we get the same thing. It's not a linear response. So the simplest nonlinear circuit is a simple comparator where we would take some input voltage V in and we would apply that to one of the inputs of the amplifier, and we'd connect the amplifier with no feedback. So we'd use the natural internal gain of 100,000 times to basically amplify the difference so much that depending on the value of V in, the output either swings completely positive or completely negative. Now in this one here, you can see that what I'm comparing V into is 0 volts. So we would call this a comparator with a zero reference. And the output basically, as soon as you are positive, because it's going to the positive terminal, you would get the maximum V out, which is the saturated voltage of the upper transistor. And as soon as this goes negative, then it would be less than the negative input, and you would get minus VSAT, the most negative voltage that the op-amp could put out. Now in reality, in this point here, when it swings from most negative to most positive, it's actually linear in this region. So that means if there's a input difference here of 10 microvolts, if there's a very, very small input that gets amplified 100,000 times, then you'll get 1 volt out. So it's still acting as an amplifier, but what we have is a very, very narrow range in the middle where you have a linear region from maybe minus 100 microvolts to plus 100 microvolts on the input. If you stay within that range, you will get an output that is not at the rails. But if you consider Vin to be something like plus 10 to minus 10, then this region in the middle is so small that we consider that it flips from the positive to negative output. Now you don't have to tie the Vin to the positive input. You could flip these inputs and tie the Vin to the negative input and the positive to ground. Then what would happen is that when this goes positive, the negative terminal is greater than the positive terminal, and the output would swing to the most negative value. So if you've hooked it up this way, you would get the flip response on the output. When you have a positive Vin, you get a negative V out. And when you have a negative Vin, you'd have a positive V out. So you can use the comparator with a zero reference to basically invert a signal, or you can create a signal that's in phase with the input. So the textbook has a separate section for comparators with a zero reference and comparators with a non-zero reference, as if there's something special about the fact that you're comparing to something that's zero. And in reality, that's not true. They're the same circuit and they do the same thing. You're just applying a different comparison voltage. So here we have part of figure 20-11, and they're showing a comparator with a non-zero reference. So let's say that this thing is powered by plus minus 12. So that's minus 12 and that's plus 12. If these guys are both 1K, then we'd have minus 6 volts in the middle, and we would be comparing whatever is coming in over here would be getting compared to minus 6 volts. And when it's greater than minus 6, the output would be positive, and when it's less than minus 6, the output would be negative. And that's shown on the graph. So the reference has moved into the negative part of the graph because it's now happening at minus 6 volts instead of 0. And when you have a voltage applied to Vin, which is greater than minus 6 volts, then the output is a positive voltage, and it goes up to the upper rail. The upper transistor turns on, and you get the most maximum positive voltage out. And if you go below minus 6, so if you go to 5.9999, and then the positive terminal will be less than the negative terminal, and you will get the most negative voltage out. So it's exactly the same as the comparator with a zero reference, except we've changed the reference voltage. So here's an example circuit of how we could use a comparator. This looks like a zero crossing detector. If you're using the 60 hertz sine wave coming out of the wall to do some timing, you could take that 120 volt signal, and if you had a large resistor like 100k ohm to keep the current down, you could put that into a couple of diodes. So a large sine wave coming in at this point here, when it's very positive, this diode would hold it at 0.7. And then when it was very negative on the input, so when it's very negative and very positive at those points, those diodes would clamp this point at plus 0.7 and minus 0.7. And that's enough to make the negative terminal greater than 0 on the positive or less than 0. So when the input is plus 0.7, the negative is larger than the positive, and you would have a negative out. And then when it's minus 0.7, you would have a positive out. So this would be an inverting output. When this input comes in like this, the output would be the inverse of that. It would go negative and then positive. And you could use this to count the 60 hertz frequency on the line and update a clock. Now, one of the problems with this circuit as it currently sits is this might be going between plus and minus 12 volts approximately. And I can't take this minus 12 volts or the plus 12 volts and tie it directly to a microprocessor. So I might have to condition that signal to be between 0 and 5 volts before I can tie it to a microprocessor. And here's an example circuit to take that plus minus 12 volts and turn it into something you could connect to a microprocessor. So what we could do is we could take this point here and tie that to our microprocessor. When the output of the op-amp is high, it turns this transistor on like a switch. This is a field effect transistor, but basically we're going to use it as an on-off transistor. So if I turn it on, it pulls this point to ground, which is 0 volts, and the microprocessor is just fine with the 0 volts. But if I pull the input to the transistor low, so if I take this down to a negative voltage, then that transistor will turn off and I'll have an open switch between these 2 points, and the switch will no longer control the voltage on that point. This resistor here pulls that point up to VCC, which we can say is 5 volts, so that means we're putting 5 volts on the micro. So we have 0 volts on the micro, or we have 5 volts on the micro, and it's fine with either one of those. So here's another example of how we can use Zener diodes to limit the output of an op-amp to within a smaller range. There's a bit of an issue with this circuit in that it needs a current limiting resistor here to work, and the reason for that is that this is a negative feedback circuit. If we put a couple of diodes in here from the output back to the negative terminal, then we've created a negative feedback circuit that is stable under certain operating conditions. So let's take a look at what happens. So if you apply a signal to the input, let's say 25 millivolts, then the op-amp will adjust the output in order to maintain this point at 0 volts, because it has to be the same as the positive terminal, which is tied to 0. That means a little bit of current flows into the comparator circuit. It can't go into the input of the op-amp, so it's got to bypass it and go around to the output here. So this point needs to fall to a voltage that holds the negative terminal at 0 volts. And if we have a 4731 op-amp, if we have current going this way, this guy has 0.7 volts, and the 4731 in reverse bias is 4.3 volts. That means the output needs to fall to minus 5 volts to hold the input at 0. So when the input is positive, the output falls to negative 5 volts. And when the input goes negative, the output rises to plus 5 volts in order to maintain 0 volts on both inputs. So we get a very small swing on the input, and we get an output swinging from plus 5 to minus 5. Change these Zener diodes, and you could have it going from minus 10 to plus 10. You could select what voltages you want to limit the output to. So this idea of taking a large input swing, let's say 120 volts AC RMS, and reducing it down to a 0 to 5 volt pulse that can be accepted by a microprocessor, this seems like something we would want to do a lot, and that there would be custom built parts for this purpose. And there is. There's a special type of op-amp which is designed and sold as something called a comparator. So if you're going to do a search on DigiKey, to find these you would search for comparators and not just op-amps. And the LM339 family is a good example of those. They can be used in a single supply or a split supply operation, and they will convert a wide range of input voltages to a smaller range. When you look at the schematic diagram of a comparator, it looks pretty much like an op-amp. Inside, it looks like 4 operational amplifiers with a non-inverting and inverting input. And you wouldn't know the difference by just looking at this. You have to look at the schematic of the internal transistors to see the difference. And that's shown here. So you can see on the input side, you can see the differential pair. So that's the same as an op-amp. But on the output side, you see that there's only one transistor on the output, and the transistor is a switch to ground. There is no upper transistor. There is no PNP transistor that can pull the output high. So this op-amp can only pull the output low. In order to get a high, what you need to do is connect this externally to a pull-up resistor and some other VCC. And now the output will go to that level when this transistor is open circuit. So this can be used to convert large voltage swings to a range that is determined by the negative supply and this VCC, which is external parts to the comparator itself.